Hello, everybody. Welcome back to class. First class of the week. Got a big group so far in the chat, I guess would be what you would say. So say hi if you're here. We only got a few more weeks of class. It's exciting, I guess. Jax, hello. Navik, good to see you. Morning, Jonathan. Morning, Jared. Hello, Molly. Molly and Navik both went to linear algebra this morning also. They must be going for the double. Reagan, good to see you. Mr. West 39. Hello. We'll get started in about a minute or so. And if you're strolling in, feel free to say hi. Good to see you, Turner. Yo. All right. Well, it's 10 o'clock, so we should get started. So I hope everybody had a good long weekend. Not that it was probably the same as all of your other days. Good morning, Nicole. But if anybody would like to join me in the simultaneous sip, first one of the week, now we can do it. All right, let me see in the chat who sipped and who didn't sip. Okay, my linear class did not tell me who didn't sip, but I want to know. Come on, embrace it. If you didn't sip, embrace the fact you didn't sip. All right, everybody went with the sip. I'll have to contact your siblings to see if this is true. Johannes went with the long sip. Okay, so we're going to continue. We're going to continue working on this area under the curve type problem. We'll improve our notation. And, ooh, I sipped twice. We'll improve our notation, and hopefully we'll get to a few examples. Okay? So the area A of the region S that lies under the graph of a continuous function f is the limit of the sum of the areas of the approximating rectangles. Okay, what is this saying? Well, in math terms, the area under the curve, and I'm not sure how much space we'll need to write out this formula, so I'm not going to draw a picture yet, but we'll get there in a second. The area is equal to the limit as n goes to infinity of f of 1 star delta x, and I'll write out what these stars mean in a second. F of 1 star delta x plus f sub 2 star delta x plus all the way up to f of x sub n star delta x. These x1 star through xn star are the sample points. Remember last class we had right endpoints versus left endpoints? So for example, we had right endpoints of our subintervals. We used left endpoints of our subintervals, or we could use midpoints, or we could just use any point we prefer in each of the subintervals. Okay, so just remember what this looks like. Here we had some graph f. And we wanted to find the area under this curve. So let's say maybe the right endpoint is our first sample point. And let's say just maybe the midpoint could be our second sample point. Then the left endpoint, and then the right endpoint again. Okay, so what we would do is we would take the limit as the number of rectangles goes off to infinity, and all this error, all these regions that kind of get counted for no, just because of error, would vanish. And we're going to be left with just the exact area under the curve. Okay, and again, throughout this class, because this is still a little bit theoretical what we're dealing with here, type any questions you may have in the chat, just because it's important to have a strong foundation with this. We often use sigma notation. To write sums with many terms. Nicole, I see your question. I'll answer it in a second. Oh, okay. We have a lot of questions. Let me just finish the sentence and then I'll answer. Okay. First, Jack says, what does delta x represent? Delta x is the width of our subrectangles. Okay, so each of our rectangles has width delta x. So this is like the height of the rectangle times the width. Height times width. Height times width. Okay, what do the stars mean? It's just notation to keep track of that we're using some sort of sample point. So it's not terribly important, but it's saying these represent the sample points that give us our heights. So we used in our example last time, we used the right endpoints as our sample points. They told us what the height was. Or we also used the left endpoints to tell us the height. We could also use midpoints, or we could use some sort of combination of them. It's just to say that we're taking these to be the points that tell us what the height is. It's not terribly important to have the stars there. It just kind of represents that we're using this point to determine the height of the entire rectangle. In fact, it's often I'll just drop the star, and half the time you'll see it, half the time you won't. It's not terribly important. Okay, so for instance, so we often use sigma notation. So what does that mean? Well, it looks like this: capital sigma I equals 1 to n. So what does this mean? Probably going to need a little bit of space. It says we're just going to add up the terms, starting with replacing I equals 1, and we'll continue to add until we get up to the number n of this function. So it would look like, well, the first term would be I equals 1. So f of x sub 1 delta x plus, and now we go up to 2. And we continue to add terms until we hit the number n. Okay, so instead of writing out this sum with n terms in it, we can write it more compactly using this sigma notation. Okay, so combining the definition of the area with our sigma notation, So the area under the curve is the limit as n goes to infinity of the sum. So when the way you would read this is the sum from I equals 1 to n of f of x sub I delta x. And so what this means is it's exactly this. Here again, I dropped the stars, so it's just a notation thing. It's not terribly important. Okay, I think it's a good time to look at an example. So let A be the area of the region that lies under the graph of f of x is equal to cosine of x between x equals 0 and x equals some number b, which is less than or equal to pi over 2. And the question is, and we'll sketch a picture of what this looks like. Using right endpoints, find an expression for A as a limit. So our region, so our function is cosine of x, or f of x equals cosine of x. So it does something like this. Here's pi over 2. And let's say B is somewhere here. So we want to find the area of this region. Okay, so it's going to be in terms of B, I'm assuming, at the end. Okay, so let's just walk through this together because, again, these questions, you'll get better at them with practice, but we haven't really had much practice. That being said, I do recommend you take a look at, I have a few videos from last semester with Riemann sums or with these sigma notations. And so I'd recommend taking a look at those at some point just for some extra practice. Okay. So let's work this out. Okay, so our number line, basically, let's just take a look at our number line. We're going from x equals 0 to x equals b, and we're going to break it up a bunch of times. So we're going to break it up into n rectangles of equal width. So my question for you is, what is delta x? How wide is each rectangle? So we have our entire interval goes from 0 to b, and we want to break it up into n subintervals of equal width. How wide must they be? Yeah, exactly, Jax. We'll find that the length of the entire interval, which is b minus 0, so b, and divide it by the number of rectangles, which is n. Okay, so in general, the way you would find delta x is you find the length of the whole interval, so b minus a, and divide by n. Okay. So again, let's take we'll take our interval, goes from 0 to b. And we'll break it up into n subintervals. And what we want to do now, we're using right endpoints. Okay? So we need a nice and concise way of expressing the endpoints. Here, okay, so this has width. So each of these has width b over n. My question for you is, what is this? What is the value here? Not the function's value, but what is the x value at the first right endpoint? So you start at 0, and you go over b over n, and you end up at, well, b over n. Okay? That's the first. That's going to be our first sample point. Okay, a harder question is, what is our second sample point? Yeah, it's 2b over n. The way we get it is we take our previous sample point, and we add delta x to it. And so b over n plus b over n is 2b over n. Okay, and then we continue this for a few times until we can figure out a pattern. X sub 3, that's our third sample point. We take our previous sample point and we add delta x to it. So 2b over n plus b over n, which is 3b over n. And what we need, well, I just erased it. We need the ith. We need the ith sample point, right? Because we had, I'll just write it over here as a reminder, a is equal to the limit as n goes to infinity of f of x of the sum from I equals 1 to n of f of x of I delta x. We already found delta x. Now we need to find x sub I, and then we just plug it into our function, and we're done. Okay, so what is the ith right endpoint? The first one is b over n. The second one is 2b over n. The third one is 3b over n. Nice. Yeah, Nicole is right. The ith one is I, here just being a number, not the imaginary number, but I times b over n. Okay, so we're basically done, right? We know what delta x is. We found that. We found x sub I. The last thing we should write out, yeah, Jared. The last thing we should write out is what is f of x sub I? And that's just to replace all the x's in our function with what we have here. And simplify if possible, but that's not really, more often than not, it's best to not simplify. So f of x sub I is cosine of IB over n. Okay, so the area, and now we're done, right? We have the area is equal to this limit. And our function says express it as a limit. It doesn't say evaluate the limit. You guys don't know how to evaluate the limit at this point. I do. Humble brag. Sorry. So we have all the bits of information, right? This limit as n goes to infinity, that's always there. Sum from I equals 1 to n, that's always there. We just needed the function evaluated at x sub I and delta x. We have f of x sub I, we have delta x. We could put it all together now. So the area of this region is equal to the limit as n goes to infinity of the sum from I equals 1 to n of cosine of IB over n times delta x, which is b over n. So this limit is, if we were to have a computer approximate this value for us, it would tell us a good approximation for the area under the curve. Right? And you could program a computer to, I mean, it's not hard to have it run over a sum. You'll learn that in your first programming class. You pick your favorite value of n that's large, like 1,000, for instance, and it would give us the approximation. It'll give us the approximation of the area under the curve. What does the I equals 1 mean? So this is telling us how we're going to start counting. We start at x sub 1, then x sub 2, x sub 3, all the way up to x sub n. So this is just notation to, instead of having a sum that has many terms in it, it says start counting when I equals 1. So start counting at f of x sub 1, and then continue to count until you hit f of x sub n, which is the top. Okay, and if you were wondering what this works out to be, that's just sine of b, but don't actually worry about that, so I'm going to erase that. Okay? Are there any questions on this? We're going to do some more of these. Obviously, or it shouldn't be too surprising that this is hard to compute by hand. So we're going to need new techniques in order to evaluate these limits. Okay. Well, if there's no questions on this, we could move on. So I'm like we did with the optimization questions, I'm going to skip one of the applications here. We're going to skip the distance question. Faye Pasley Simon says, great topic. Thanks. I'm going to skip the distance question, but it's in our notes. So don't worry about it for a test or a quiz, but there may be a WebAssign question that asks you to approximate distances using this sort of sum. And so you would just treat our velocity function as we treated f in this case. But since we lost a whole week of class due to the disease, I have to cut some material, and that's one of the things I'm cutting. Okay. So let's move on to 4.2. Which is definite integrals. Okay, so let's define what a definite integral is, and then take a look at some examples. So if f is a function defined on A to B, what we're going to do is we're going to do the same kind of process. We're going to divide the interval AB into n subintervals of equal width. That width being delta x. Okay, so here, this picture still kind of works for us, going from A to B. We're going to take our subinterval, break it up into a bunch of, subintervals of equal width. And we'll let x sub 1 through x sub n be sample points in our interval. Okay, so this is all the buildup. We have a function that's defined on some interval. We take our region, break it up into a bunch of subintervals, take some sample points. Then the definite integral of f from A to B is, I'll write it up here because it's important. Okay, so this is, we write the integral from A to B of f of x dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. Okay, so we replace, if we have this, if we have the limit as n goes to infinity of this sum, we replace it with the notation here. And the way we read this is it's the integral from a to b of f of x dx. And then just note, if f of x is greater than or equal to 0, then this is just the area under the curve. Yeah, so dx here is just saying, it's the right idea. Dx here is telling us what variable we're going to be taking the integral with respect to. Okay, but yeah, so here delta x is going to have some sort of value. In our previous example, it was b over n. When we write it in integral notation, it is just going to be treated as, it's like basically the integral sign and dx are kind of paired together. This will not have a value to it. It's always just going to be dx, unless you're in a different, if you're in like Calc 3, then you may have a dz or dy. I guess we may see a dt, but yeah, this tells us which variable we're taking the integral with respect to, where in this case, this was actually just some number. So this is a value. This is just kind of a, it tells us how to take the integral. Hopefully it becomes clear when we do an example. Okay, but yeah, this is just notation at this point. So the bits that we'll have to fill in, the left endpoint, the lower bound of our interval, the upper bound of our interval, and the function. The squiggly sign and the dx will stay there every time. Okay, so my question is, okay, so if f of x is always non-negative, so on the x-axis or above, this represents the area under the curve. My question what does the integral from a to b of f of x dx represent if f takes on both positive and negative values? Okay, so if we had a function like this, if we had a function like this and we wanted to evaluate this integral, again, we're going to be looking at, f of x sub I. We'd take our region, we'd break it up into a bunch of smaller regions. Sometimes f of x sub I will be positive, so we'll be adding some positive numbers. At other times, we're going to be adding some negative numbers, right? So we'll have some positives coming over here, and then adding in some negatives, and then adding in some positives. And so my question for you is, what results? what is the result of adding some positives, adding some negatives, and then adding some positives? Right, so if we tried to write out this sum here, sum of the terms, right? These guys would be positive, these guys would be positive, these ones would be negative. Yeah, that's exactly right, Jax. What we're going to do is just treat it as like 3 separate regions. Treat this as a positive area, treat this as a positive area, and then treat this as a negative area, whatever that means, and then we'll just take the difference. So it'd be like your positive area minus your negative area. So if A1 is the area of the region above the x-axis, and A2 is the area below the x-axis, then the integral from A to B of f of x dx is equal to the positive area minus the area below. So let's state a theorem and then we could get to an example. This theorem tells us when these integrals exist. So if f is continuous on the interval AB, or if f has only finitely many jump discontinuities, then the integral exists. What we write is we say that f is integrable on AB. All right, so let's take a look at an example. And if you like this example, you are going to love the video I posted on YouTube yesterday because they're almost the same. Okay. So if you want to see another example like this, I mean, those of you on the notification squad, you already knew that I posted this video, but some of you maybe are slacking and weren't sure. The video I posted on YouTube yesterday is just like this one. So express the limit as n goes to infinity of the sum from I equals 1 to n of x sub I to the third plus x sub I sine of x sub I delta x as an integral. On the interval 0 to pi. Okay, so basically what we want to do here is we want to just switch from this limit and sum notation to the integral notation. Okay, so the bits of information we need A, we need B, and we need f of x. Does somebody want to share what A and B are in this example? And if you really want to, does anybody want to share what f of x is in this example? Yeah, so A and B, I think Jax is the only one that has a working chat, it seems like. I'm teasing you, Jax. A and B are the boundaries of our interval, right? So they were given to us. Sometimes they're not given to us, and we'll have to find them. But A and B are the boundaries of our interval, so we can just read them off immediately. 0 and pi. And then to get the function, well, it's anything that's it's everything that's multiplied by delta x. And instead of having x sub I, which represent our sample points, we'll just treat them as the variable x. So it's x to the third plus x sine of x. Okay, and so we're done. So this limit, the limit as n goes to infinity, of the sum from I equals 1 to n of x sub I to the third plus x sub I sine of x sub I delta x is equal to the integral from 0 to pi of x to the third plus x sine of x dx. Okay, this tells us which variable we're integrating over. Okay, and we don't know what this number is. We know that it is going to be a number based on this previous theorem, right? Because we have a continuous function, right? It's a product of a polynomial and a trig function. It's going to be continuous, but or a sine function. We don't know what this value is. Maybe some of you do, if you took AP Calc last year. But even if you, it'd take a few minutes to compute. Yeah, so this example is just a practice going from our limit notation to our integral notation. Okay? So I think that's a good place to stop. I'll hang around and answer any questions you may have in the chat. I have office hours today at 1. I know there's not much WebAssign due tonight, but there's going to be quite a bit due next week. So if you're done with the homework, might as well get started on it, especially while it's fresh in your mind. Okay, so are we spending, I'm assuming, another day on this content? Yeah, we just got started with this, Jared. Yeah. We're just scratching the surface of 4.2. There's quite a bit in this section. But 4.1, you're good to 4.1, you're good to go. Are we working our way up to solving this integral? Yeah, well, that's going to be the big goal. We'd love to be able to solve these integrals. This one in particular, we won't be able to. That one is, you're going to have to wait for Calc 2, but we'll be able to solve some of these integrals. Okay, remember, before you leave, like button equals smashed. I don't know if you saw this, but I passed another big milestone this weekend. 700 subscribers. Only 300 left until we hit the big 1,000 mark. Faye says, nice. Faye was one of my earliest subscribers. So it's nice to see that she's still joining the live streams every once in a while. All right, well, if you don't, oh, here we go. Jared asks, how many subscribers did you start with this year? I had like 120 at the start of the semester. And then once classes went online, I quickly went from 150 to like 500, and then it's been trickling up ever since. Chat don't work. Turner, it works. I see what you're saying. Faye says more like COVID 700. Yeah. Yeah, good one. Yeah, it's gonna be sweet when we pass 1,000. All right. Unless there's any last minute questions, I'm going to sign out. All right, thank you all for coming. I'll see you tomorrow. Bye-bye.